In this example, we are going to see how we can design a multiplexer using logic gates. So again, we won't do it as a general case of combinational design because a multiplexer, even a 4-to-1 multiplexer, is already a circuit with 6 inputs, 4 data inputs, 2 selection inputs, and then it's a circuit, it's a function that depends on 6 variables. Doing it with a Carnot map will be a bit difficult, okay? Actually, we don't need that because we already know that the multiplexer is a selector, so it corresponds to this function. This function we can obtain not by simplifying a Carnot map, but by thinking about the specific operations of a multiplexer. So we build that expression so that when S1, S0 are equal to 0, 0, okay, then what we have is that only this term will activate because this is a 1, this is a 1, so here and all the other terms will be 0 for any reason. For example, this is 1 but this is 0, so this term gets out of the equation. This is 0 and this is 1, so this term gets out of the equation. And here both variables are 0, so it gets out of the equation. So in this condition, it is z equal to this 0. So that's the way this function makes the selection operation in the multiplexer. So for each combination of S1 and S0, only one term in the multiplexer expression activates. And that term makes the output to be equal to the remaining literal in the term, which is the corresponding input. Actually, we have in each term, we have one of the possible combination of the selection inputs. So if you look at this, what we really have are the minterms, all the possible minterms of the selection inputs multiplied by the corresponding data input. So z is equal to actually m0 times the 0 plus m1 times the 1, m2, d2, m3, d3. Okay. So this idea of the multiplexer give us another idea is that the design of the multiplexer is actually very similar to that of the decoder because the decoder generates all the minterms and then we only need to multiply those minterms by the corresponding data input and then put everything together with a NOR gate. Okay, so this could be for a regular 4-to-1 multiplexer. What if we want to add an enable signal? Simply an enable signal, we can add like an additional signal to the design, meaning that if now we want Z to have this value only when the enable is active, okay, we can simply multiply all the expression by the enable signal. Okay, we want the enable signal to be active low, so we complement the enable. The idea is that this is the regular operation of the multiplexer, but it will only make it to the output when enable signal is 0. So we have an active low enable. Okay. Now we can build our circuit just by using the right expression. Okay. We could, for example, we can start. Let's give two options. Okay. So this is just actually for case B. In case A, okay, we don't really need the enable, but we will need to generate the function for a multiplexer that is 8-to-1. So it has 8 data inputs. It will have 3 selection inputs. Okay, so it's actually the same, only that now my expression will be a bit more complex, because we will have all the minterms that we can build with 3 selection inputs. So we'll have a minterm 0 times d0 plus minterm 1 times d1, and so on and so forth, up to minterm 7 times d7. Okay, it will be an expression like s2, s1, s0 all complemented d0 plus s1 complemented, sorry, s2 complemented, s1 complemented, s0 times d1 plus s2 complemented, s1, s0 complemented times d2, and so on and so forth, up to s1, s2, s0 times d7. Okay, and from here we can draw the circuit right away. Okay, we use a structure like in the decoder, and multiply by d0. This is and we make the complements. This is AND gate, AND gate, AND gate, AND gate, and then we sum everything together. Or we can use NAND gate, NAND gate, NAND gate, NAND gate, and add everything with another NAND gate. Okay, but I prefer to do it with case B, which is a bit more complex because we have added the enable. So in this case, it's basically the same. We build all the minterms or of the variables. We have only 4 minterms, so we have S1 and S0. Okay. And let's draw the circuit more or less. First we draw lines for all the signals. We have S1. We'll put S1 complemented here. We will put S0 here. S0 complemented here. And we have the inverters here. Okay, and now we will have to do the products. And to do those products, we need 4 AND gates. We draw by 4 AND gates. I think I will need these lines to be a bit longer. Make them longer right now. Let's see. Okay, and just draw my NAND gates, my AND gates. Okay, this is the AND gate, given the first output, the second output, third output. Sorry, not output, but terms. Okay, this way we generate these four terms, and then we will have to add all the terms with an OR gate. Great, this will be the output of my multiplexer. This will have to be connected here. Now these terms are the first minterm here, as it would be as in the expression here, S1 complemented, S0 complemented, very similar to what we did in the decoder. So we have S1 complemented here, S0 complemented here, but now we have to add in together with the first minterm of the selection variables, we have to add D0, the data input. So we have our data input D0 coming here. Okay, so this is D0, D1 will be around here, D2 will be around here, and D3 will be around here. So we only need to make the connections. To create first minterm 1, it's 0, 1. So it's here and here. And we multiply it by D1. Now we have a 1, 0, so if we have S1, S0 complemented, and D2 here. Great, and now we have D1, S1, S0, and we have D3 here. Okay, so that will be the design for my regular multiplexer. Okay, this will be a multiplexer, this part of the expression here. Okay, only this part of the expression here. Now we need to add the enable, but we can add it in two different ways. If you see, we have in this form here, we have considered the option to generate the regular output of the multiplexer and then enable it or not using this signal here. So we can modify our design just to add that signal using an additional AND gate. Take that result here and use an AND gate here. Let's do it like this. And here we will have our enable signal that comes complemented. So we add an inverter. Okay. So this approach is like a fix. We implement a regular multiplexer. Now we fix it to add the enable signal. When the enable is equal to 0, this will be a 1, and then Z will be equal to the regular function of the multiplexer. When E is equal to 1, I have a 0 here, and the 0 will make the output to deactivate. Okay? But it's a kind of a fix. It's not really very convenient, because by adding an additional AND gate, we add an additional level of gates to my circuit. You see, before we have complements, gates, and the output. We had a regular 2 levels circuit plus inverters. Now we have 2 levels plus a 4th level here with this fix. We don't really need to do it like that. I don't really like this solution. Okay, probably if you already have a multiplexer, like in the old times, you had a circuit already done, you need to add an enable after fabricating your multiplexer, it may be a good solution, okay? But it's like a quick hack now. So you don't really need to do that, because you can include the enable inside the expression. So you can have your enable M0 D0, okay, like you have in the slides for the case of the multiplexer with the enable here, okay, in the expression here. Only that now our enable is complemented. Okay, this is the only difference with the one in the slides. So once you include the enable in all the terms, so basically you have the same result than before, but including this enable M3D3. Okay, so all we have to do is to include enable in all the terms. I quite ran out of space in these NAND gates, but I'll try to do it. So I will put the enable here. It had to go through an inverter because it's complemented. One inverter is enough to generate the enable for all the cases. And now I will make my gates a bit bigger so that we have room to include the enable. Okay, this could be enough. It's probably like that and like that. Okay, more or less to get the idea. So yes, it's a matter of connecting the enable, adding a connection to the enable to all the gates here. This one here, this one here as well, and this one here. Okay, that's it. Multiplexer with enable. Again, the main purpose of this example is to show how the multiplexer has a function that we can see at the high level. It's a selector. It's a very useful device. It's my favorite combinational digital device. It's very, very useful in many applications that we will see along the course. But it's not something that is mysterious. It corresponds to a very simple expression that can be simply done. It's a sum of product that can be done with gates. It's not a mysterious device or anything, only that once we know that it's easy to implement, so we can implement. The good idea is that we can implement a multiplexer no matter how many inputs it has, because if we have more inputs, then we simply have more midterms, we have more terms, but the way it's implemented does not depend on the number of inputs, because we don't have to solve complex Carnot map. We can use the regularity of the device in order to find a way to implement the multiplexer no matter how big it is. And we will see that once we have multiplexers, we can use them to solve problems in a much more easier way. Okay, that's it. Thank you.